So let's talk about this magic configuration, the solenoid. Okay, and now the solenoid is a very practical and very nice way to create uniform magnetic fields. And it's actually easy. You take a nice cylinder, let's say it has a radius r and some length L, and you take a wire and wrap it around this cylinder. It takes a while to wrap this. And you send some current I through this. And let's say in total there are n turns of wire. So what I would like to calculate is the magnetic field inside the solenoid. And as you can see from the previous example, this is really not too different from what I have drawn. Think of the previous question, infinitely many wires carrying current I towards me here. If I actually take this one direction and fold it onto itself, what do I have? I have a current circulating on the cylinder, which is pretty much like a single wire that's wrapped on this cylinder carrying current I. Okay? So what am I going to do? I'm going to calculate the magnetic field inside the solenoid. Now my hope is that because the magnetic field was uniform for this infinite configuration, hopefully when I fold it up into a cylinder, magnetic field will remain uniform inside my solenoid. All right? Now, again, I'm going to do this approximately. Okay, I will think that this wire is wound very tightly. So maybe if I actually look at the details of the magnetic field, there will be wiggles here and there. But if the wire is very tightly wound, then those wiggles are not going to be very important. All right? Now, how do I find the magnetic field inside the solenoid? And for that, maybe I should think about how magnetic field adds up. One way to think of the solenoid is this compactification of the plane, or another way to think of it is I have many current loops that are added on top of each other, right? Like a stack of coins. So which way is the magnetic field pointing inside the solenoid? Inside the solenoid, it's obviously the same as the previous case. If my current is going like that, and on the other side it's actually in the reverse direction, right? Then, how did I calculate the direction of the magnetic field for a loop? I put my 4 fingers on the direction of the current. My thumb actually showed the loop here. So I can do the same thing for the solenoid. Here is my solenoid. I'm putting my 4 fingers onto the current direction. My thumb shows the magnetic field direction inside the solenoid. So the magnetic field will be hopefully uniform and to the left inside the solenoid. How about on the outside? Remember, this infinite plane created equal current up and down. What happened when I actually turned it into a cylinder? It's like I had actually, if I had two infinite planes, what would be the magnetic field? They would cancel in the outside regions. It would only be confined to the inside region. Okay? So it's pretty much like that. And the way to think about it is that magnetic field lines were a little bit different from electric field lines. Electric field lines started on charges and ended at charges. But there is no such thing as a magnetic charge. When you split a magnet, you get two smaller magnets. You always have north and south pole together. You don't have isolated north pole, isolated south pole. So magnetic field lines close onto themselves. Okay. So these field lines on the inside, they must close onto themselves. So what do? They go uniformly through this cylinder, but then they will actually connect to themselves outside the solenoid. So if the solenoid is long enough, it's very long, the magnetic field on the outside will be extremely small. Okay? For a long solenoid, outside magnetic fields, these are called, just like for the capacitors, these are called fringing fields. Okay. They are sort of leaking from my solenoid. They are small for a long solenoid. So here's what I'll do. I'll make the following assumption. I'll actually say that magnetic field is uniform inside and it's zero on the outside. That makes sense if I have a long enough solenoid which is very tightly wound. Alright? Let's try to find out the magnetic field inside my solenoid. How am I going to do that? It's possible, but actually quite hard to do this by Biot-Savart's law. Add up all these pieces of current. Gets nasty in 3 dimensions, right? But I can use Ampere's law if I assume that my magnetic field is constant on the inside and zero on the outside. And that's not a bad assumption. So here's what I'll do. I'll take a Ampere loop like this. Question? Good. I'm saying for a good solenoid, it's almost infinite. Its width is very small compared to its length. Okay? Now inside the magnetic field is uniform and it's dense magnetic field lines. But how do they come back onto themselves? They actually go to the edge of the solenoid. If I actually make the solenoid infinite, they will never escape. Okay? But if the solenoid is long enough, there will be a magnetic field on the outside, but it will be very, very small. Okay? That was a good question. Any other questions? No? So, let me take a cross section of this. Let me redraw it. So, I'm taking a cross section of the solenoid. On the top of the solenoid, all my currents are going in. It's a single wire, but that's what it is doing. And at the bottom, all my wires are coming towards me. And here is my Ampere loop. Now, I'm going to calculate B dot dl. And again, I'm going to separate it into 3 parts. No, 4 parts. I3. 4 parts. Now, what did I assume? I assume that the magnetic field is uniform on the inside and it's 0 on the outside. On sides 2 and 4, what is B dot dl? Why? Because even if the magnetic field exists, it's perpendicular to dl, right? On side 3, what is B dot dl? On the bottom side, what's B dot dl? Why? There is no magnetic field. When B is 0, B dot dl is automatically 0. B is 0. So all of this B dot dl actually is coming from the top, from the inside region. And on the first part, on the top of my ampere loop, B is parallel to dl. So this is just going to be B times whatever is the length of my ampere loop. B times L. How about I in here? Let's go to a better. Which currents are inside my ampere loop? Well, only the ones which are here, right? How much current is passing through my loop? Let's do a simple proportionality. If the total length of the solenoid was L and there are n turns, how many turns are there per unit length? N divided by L. So how many wires are there inside this region? The number of wires? Well, I call too many things L. Let me call this something else. I'm going to call this L, small l. N times small l, and each wire, it's actually the same wire going through the system. They are carrying the same current times I, right? Then integral B dot dl is mu 0 I in. Integral B dot dl is B times the length of my ampere loop. Mu 0 is mu 0, I in is N times small l times I, which canceled each other. So the magnetic field inside the solenoid is mu 0 times N times I. But what was this N? It's the total number of turns divided by the length, or turns per unit length of the solenoid. Now this is pretty interesting. First of all, it's really nice that we have a uniform field. It's somewhat expected that it's proportional to the current here, right? More current, I should have more magnetic field. But it's also proportional not to the total number of turns, but how dense these wires are wound on my solenoid. So actually, if I'm lazy, if I'm winding it loosely, I will not get very good magnetic field. But if I'm not lazy, if I make sure that I wind my wire very, very closely, then I will get more magnetic field. In the old days, 25 years ago, when I was an undergraduate student, if you need the solenoid, you need to go to Konya Sokak at Ulus, which is where they sell all these components. But you could not buy a solenoid. There are people, there were masters of solenoids, usta. Okay, so you went to the usta and said, wind me a solenoid, and he'll say, what should be the length? And this guy was really good at winding wires. He was very careful. He did that by hand. Then someone invented a nice machine which does it, so the usta went out of his job probably. But so that was a skill. I mean, how to tightly wind a wire around the loop, because the more tightly you do it, the more magnetic field you'll have inside your solenoid. All right? Good. Now, here's the thing. Of course, this is nice. A solenoid is nice. And I'll be lazy. I'll just say, okay, I've wound it like this. There's a magnetic field here. And some people said, hey, can we use that? Now what? Okay. Let's go back to the previous chapter. Do you remember what happens to charged particles in a uniform magnetic field? What did these charged particles do? Yes. They went in circles, right? So someone said, hey, why don't I take my charged particles and put them inside the solenoid? If my magnetic field is large enough, they will just keep going in circles. Okay? And this is actually very good. Even if these particles are very, very hot, so they are moving at very high velocities, they'll still keep going in circles. So maybe I can use a solenoid to store very hot charged particles, which is otherwise known as plasma. Okay? What's the sun made up of? It's made up of plasma at millions of degrees. Right? So people said, hey, maybe I can use a solenoid to store very hot gas or very hot plasma charged gas. Okay? And then of course they immediately realized, well, maybe that's not the best idea, because you'll not really be going around the circle in 3 dimensions. You'll actually going around these magnetic field lines, but you'll have a corkscrew. Question? No question. Right? So you will actually eventually escape from your solenoid. So people came up with some ideas to put caps here. I said it's called a magnetic bottle. So if you can make a magnetic bottle to store your charged particles, that's also very nice. That's fine. But these caps, just like if you have a Coke in a bottle, there is a cap, but if you shake it hard enough, that cap is going to blow off. Same for these magnetic caps. If your plasma is too hot, the particles will escape from this. So another guy said, hey, here's my solenoid. The particles are escaping from these ends. Why don't I kill the ends? Why don't I take my solenoid, turn it into a donut? Okay? Why don't I make something that looks like a simit? Okay? What's the do not in any way go and tell your grandmother that you studied simit in your physics 102 class. She will not be impressed. Tell her that you studied a torus. A torus is what ancient, probably Latins called simit. Okay, so it sounds much better. So he said, okay, instead of doing a solenoid, I'll take my wire. Let's take the wire with another color. Go down to we'll go down to Mozart Cafe, buy a simit, and take our wire and basically wind it around our simit. And this configuration is called a toroid. And that, it turns out, is one of the best ways to store plasma. Now, there's a big push in the physics community for the last maybe 40 or 50 years to create a fusion reactor. Now, fusion and fission are both nuclear processes, but fission is when you take a big nucleus and you split it into smaller nuclei. Okay? That's how our usual nuclear reactors work. You take some big nucleus like uranium, plutonium, you break them up in a controlled fashion, and the heat during this breaking up turns your turbines, boils your water, that turns your turbines, that generates your electricity. It's good. Unfortunately, it's a runaway process. Right? So if you get the ratios wrong, something goes wrong, a tsunami hits your reactor, what you get is basically a runaway process. It's an atomic bomb, okay, more or less. So that goes off, okay. So you don't want that. And it turns out it's also not very efficient. That's not how sun generates all the heat. The sun does the reverse. It takes very, very light nuclei. What are the lightest possible nuclei? Hydrogen, right? Just a single proton. Maybe add a few neutrons there, make deuterium, tritium. If you actually collide two hydrogen atoms, two hydrogen nuclei at very high velocities, well, 2 is not enough, but if you collide 4 of them, or sometimes 3 of them, you get a helium nucleus. And that creates a lot of energy. So you take basically hydrogen collision. I don't know how to draw a hydrogen collision, okay? And you make helium. Helium-4 or helium-3. That's how sun generates its power. So the idea is, hey, why should we be, slaves to the sun? Let's have our own sun. Let's take a magnetic bottle, put plasma in there, which is as hot as the sun, so that it generates energy, and that energy we can use. Now, right now, the situation is as follows. We have to heat this guy, right? We have to heat this plasma. There will be some loss of heat because particles are escaping. This loss of heat is more than the power generated by our plasma. So it's actually, it's not even inefficient, it's actually taking in power. Okay? So that's a science experiment. Now, and these things, these fusion reactors models, it takes a lot of effort to build, a lot of money to build them. But some guys said, hey, let's pull our resources together, let's make the international tokamak reactor. Okay, tokamak is a name for this toroid plasma confinement systems. Okay, was found by some Russian guys. That's why it has such a nice name, tokamak. So, and this thing is being built in France now. Everyone, except of course Turkey, is a partner to that. Okay. No, I mean all the developed countries are partners in this effort. And actually, last year the director of ITER gave a talk at Bilkent. It was one of the colloquium of the physics department. You were probably not here, but they plan to, by 2025, 2030 latest, they actually plan to generate electricity in that and show that such a thing is feasible. Okay, there is a rival effort by a small group in Germany. Their design of the reactor is still a torus, but it has different magnetic fields, and maybe they feel they can actually do it earlier. But I think within your lifetimes, you'll see this as a serious challenge to all other energy generation efforts. So obviously we will not be able to calculate the magnetic fields and what happens to the plasma inside the tokamak, but let's do the following. Let's actually take a simple toroid and see what the magnetic field inside looks like. Okay? So let's talk about a square toroid. So here's what I'll do. I'll take a toroid with a square cross section. Okay. Maybe I should draw some of those. All right. So this length is L, and this length is also L, and this radius is small r. So does everyone understand the geometry? I have a square that's rotated around one axis. Okay. Now, here is the thing. I'm not going to draw this, but n turns of wire are wound around the square torus. The wire is carrying a current I. Find the magnetic field inside the toroid. So how is the wire wound? Let's say that, okay, I said I will not draw it, but I'll attempt, and it will make the figure worse. So it will actually go so it's wound so that the current is going up. I'll do one more turn here. The current on the top is going in. Okay. So the question is, which way is the magnetic field in this object? How did we find the magnetic field for a solenoid? We took our four fingers, put it on the direction of the current, our thumb showed the direction of the magnetic field. So would anything change if I actually distorted my solenoid into the torus? No. So there should be a circulating magnetic field inside this object. So why is this nice? Now all my magnetic field lines are closing onto themselves inside this toroid. Okay? That's why magnetic charged particles following those lines never get out. All right? Good. Now, here's what I will do. I will actually plot a cross section. But not a cross section in the xy plane. I'll take a cross section in the xy plane. I'll look at the system from the top. Okay? So what I'll see is an internal radius and then out radius. Now, the current, if I cut this like a, not like a cake, but just from the middle, okay, the current is going in on the inside radius and it's going to come towards me on the outside radius. Who is comfortable with the geometry now? Can you imagine? Okay. I think one of the hardest parts of this Physics 102 course is imagining all these three-dimensional objects. So, which way do I expect my magnetic field to circulate in this? If I take my 4 fingers, I'll try to do it in the direction of the current loop. The current loops are so that they are coming towards me on the bottom and into the board here. So they are giving me this sense of rotation, which means my magnetic field will be rotating clockwise inside. Okay? Good. So I actually expect a magnetic field which is rotating clockwise here. Of course, what I'm wondering is whether those lines look so terrible, I'm going to clean them. Plot only one of them. So I would like to find out if the magnetic field inside is uniform like the solenoid. And for that, what should I do? I should actually take an Amperian loop. An Amperian loop which is a circle. I don't know what happened here. Okay. I'll say it's a loop with radius d. And its sense of circulation is the same as the magnetic field. So what is B dot dl? Although my magnetic field and Amperian loop seem to diverge at some points, if this was very uniform and if I was a good scribe, by symmetry I expect the magnetic field and the Amperian loop to be always circulating in the same sense. So I would imagine B is parallel to dl on all points of my Amperian loop by just symmetry alone. So this is going to give me 2 pi d, which is the total length of my Amperian loop, times B magnitude. How about I in? How much current do I have I in? Now my Amperian loop is here, and all the turns of wire are actually passing through my Amperian loop. So it's not a piece of the current that's flowing in the system, but all the current is contributing to my magnetic field. So maybe this time it's not so important to wind it so tightly, because all my wires, all my turns are contributing to the current. It turns out it's still important to tightly wind it, but still, now I can use my Ampere loop is mu 0 and I. So the magnetic field on the inside is mu 0 and I divided by 2 pi divided by d, and this distance should be larger than the inner radius, and it should be, let's write it where it's larger than the inner radius and should be less than the outer radius. Why? What is the magnetic field in the region here? If I take an Amperian loop like this. Why is it 0? Because no current is passing through my Amperian loop. How about on the outside, on the extreme outside? What's the magnetic field? 0 again. Why? The currents, positive currents and negative currents, cancel each other. So net current I in is going to be 0. So magnetic field will be 0 outside. So this is a really nice way to confine my magnetic field into a finite region of space. Okay? But we pay the price. Our magnetic field is actually larger on the inner radius and less on the outer radius. So it's not going to be uniform like it was in a solenoid. And that causes some problems when you have a very hot plasma. Some of these very hot particles, some of these nuclei, go and collide with the walls. Okay? When there are billions of them, when they are repelling each other. So if something at 1,000,000 degrees collides with your walls better be able to take such damage. They put certain tiles, ceramic tiles there, and they have to replace them pretty quickly. Okay, so that there is nothing burning up. Nice thing about fusion is it's not going to be a runaway process. You know, if a tsunami hits a fusion reactor, if you can generate a fusion reactor and a tsunami hits it, then it's going to just be extinguished. You know, it's not going to be radiating for the next 200 years. So it's somewhat safer. Any questions? No? Okay, let's actually solve one more example about magnetic field. So I'll have the following. Now, this is going to be an infinite system. This is called a coaxial wire. How many of you have cable TV at home? Not many of you. Everyone is using? Okay, just a few things. Okay, how about just the antenna from your dish receiver to your TV? Have you ever looked at what kind of wire that is? Did you see it cut at all? There's a very thin wire at the center, and there is a cladding, so there is some plastic material, and then there is a wire which is basically a cylindrical shell. Okay, because they both the cylinder and the small wire have the same axis, it's called a coaxial wire. Okay. So what happens there is that you actually have current that runs one way in the central wire, and this whole current uniformly goes back on the outer wire. Okay? That's how a coaxial cable works. All right. So here is the question. Find the magnetic field inside and outside the coaxial wire. Any ideas? What should we use? Is this symmetric enough to use Ampere's law? Or should we actually split it into small parts? Excellent question. You don't understand the geometry because I did a poor job of drawing it. Okay, so here is my model for my coaxial wire. There is a thin wire, very thin wire at the center, and then there is another metal, like cylindrical shell, that's around it. Okay, so at the one is at the center of the other. Okay, now current I is going up here and it's coming down from this cylindrical shell. Okay, does that help a little bit? So let's say the radius is r, okay, and the shell is infinitely thin. It's a very thin shell. Question?
Why is the current coming down? You said that it's going up, right?
It's going up in one way and it's coming down in the other way. So they are just opposite. So the net current flowing through the coaxial wire is 0. Okay. So the nice thing about coaxial wire is if you have coaxial wire like this, you can put a battery here, not a capacitor, a battery. That's your coaxial wire. On the other side, you can put a resistor, and here is what happens. Okay, current on the outer shell is one way, in the inner shell it's the other way. All right. Now we're trying to find out why people actually like coaxial wires. All right? We'll find out something nice. I have 5 minutes, so I'll do this quickly. What does the cross section look like? The cross section, I have a wire at the center and another wire at radius r. Now current, if it's coming towards me at the center, current is uniformly distributed, but it's coming, well, if it's coming towards me now, it's going away from me uniformly. So let's try to find the magnetic field inside the wire. Or let's do the following. Let's find B outside. How do we do that? We take an Amperian loop like this. Integral B dot dl is I in times mu 0. But what is I in for this loop when the radius r is larger than capital R? What's total current passing through my Amperian loop? It's 0, right? Why? The internal carried current is exactly returned from the outside. All right? So the total current is 0. The current may be coming in here, but it's exactly going back the other way and that metallic shell. All right? So on the outside, magnetic field is 0. How about B on the inside? Let's do it on the inside. Which way do I expect my magnetic field to be? How do I find the magnetic field of a single wire? Here is my single wire. It's carrying current like that. So the magnetic field should be rotating in the same sense as I've drawn. Okay. So the magnetic field will be also like that. So B inside, I'll say B dot dl is just B magnitude times 2 pi r, because B is parallel to dl. What is I in for that? There is only the central wire that's carrying current through my loop, so it's I. So this is going to be mu 0 times I in, or B magnitude, is just our usual result. So why is coaxial cable so nice? Why is it used in all antennas and a lot of other applications? Because its magnetic field is also confined into a region. Now, if I have a usual wire that's lying around, when I try to pass current through it, what does it do? One part creates a magnetic field which affects the other part. It gives some forces. It may even cause some interference. Okay? Actually, a nice way to spy on someone's electronic correspondence before the days of Wi-Fi was to take another wire and get it close to the wire which carries the telephone signal. Because of this magnetic field, you could actually take a coupling and hear what they were saying if there was no crypto, right? Right now it takes a little bit more work to do that, probably. But this is the general idea, okay? Let's take a 10-minute break, and when we come back, we'll have a quiz.